Let's take a look at example 12.9. Alright, at any instant the horizontal position of the weather balloon is defined by x as a function of t. So we have x is 8t at any given t. We also have that the equation for the path of the balloon is a function of x, y as a function of x is equal to x squared over 10. Alright, so this one is not a function of time. And we're going to need it to be. So this is reinforcing the calculus videos that I just did. So right off the bat, we're given that the x as a function of t is 8t. Let's go ahead and use that. X as a function of t is equal to 8t. And if you remember, the velocity in the x direction would then be the time derivative, or x dot. And since time is already in the equation, we just have to take the derivative. And I get 8. This tells us that the balloon has a constant velocity to the right of 8 feet per second. So its velocity is constant, its position is not, its position is at any given t times 8. Okay, but we want the velocity, we need both components if we're trying to find the magnitude, right? The x and the y. So let's find the velocity in the y direction. That would be equal to y dot, the time derivative of y. So that's the time derivative of x squared over 10, the path equation. Okay, we can get a derivative. If I take the derivative as normal, that would give me 2x over 10. And then we need to multiply that by x dot. Don't forget this part. The next step, well, we have the velocity, so we can plug in the fact that this is equal to this. And we know the x coordinate, it's given to us as 16 feet. So if we want to crank out the velocity in the y direction, we can. I get 2 times 16 feet, all divided by 10. And then the velocity was a constant 8 feet per second. And crank the handle, it's going 25.6 feet per second up. So we have its vector now, right? We can say it has an 8 in the horizontal direction and a 25, not to scale, 0.6. So the magnitude of that vector, its velocity, would be equal to the square root of the x component squared plus the y component squared. And we get 26.8 feet per second. And if we wanted to find that angle theta right there, we could say it's equal to the tangent inverse. And there's no shame, right? I literally will write SOHCAHTOA, sorry, when I do trigonometry. If it's in this configuration, I know automatically to use tangent inverse and put the y coordinate over the x coordinate. So the tangent inverse of 25.6 over 8. And remember when you're doing the tangent inverse that doesn't give you what quadrant it's in. We use the absolute value and you have to figure out which quadrant it is in on your own. And in this class, I generally measure everything from the positive x-axis. So even if we have an angle down here, I'm not going to call this 30 degrees. I'm going to call it 180 plus 30. And if you put that into your cosine, so the cosine of 210 and the sine of 210, when you break up components, the sine comes out automatically. You don't have to worry about it. Okay, so crank the handle on the tangent inverse, and we can get the angle as 72.6 degrees. So that's our answer. The magnitude of the velocity is 26.8 feet per second, and theta is equal to 72.6 degrees. Going up and to the right. It also asked us to find the acceleration, so let's go one step further. We left off with the fact that the velocity in the x direction, or x dot, was just equal to 8, and the velocity in the y direction is 2x over 10 x dot. Alright, so let's take this one step further. We need to take the derivative. I can take the derivative of the x component right away and get x double dot, or v dot, and the derivative of a constant is just 0, so it's not accelerating. We have a constant 0 acceleration in the x direction. It's just cruising. But to take the derivative of the velocity in the y direction to get the acceleration, we'll have to use the chain rule again. I'm going to call f the x and g the x dot, and we'll pull the 1/5 out. So there's your f and there's your g. Take the derivative of x, I get 1 times x dot. If I take the derivative of g, or x dot, I get just a x double dot. Alright, putting this back together using the product rule will give us an acceleration, because the derivative of the velocity would be the acceleration, v dot in the y direction, or acceleration, those are the same thing. Alright, that's also equal to y double dot, all the same thing. So make sure you recognize that. And then putting this together, I get x dot plus x double dot. So the acceleration in the y is x dot squared plus x double dot. And we know x dot was a constant 8, x is 16, and we don't even have to worry about that term because we found that x double dot was actually 0. So I get an acceleration in the y direction of 12.8 feet per second. In the x direction we had nothing. We only have a vector that is 12.8 long. That's our acceleration. Well, you could find the magnitude like this, I suppose, but you don't really have to, right? It's 12.8 feet per second squared. And then that angle, you can use the rules if you want, but where do we find 90 degrees on the tangent? Well, we find that anywhere that the x component is 0, and the adjacent component is 0. So 90 degrees is our angle. Alright, I would definitely do 12.10 on your own. It's almost identical. We will expand on this topic and you definitely need to know how to do this. You also could have expressed this in... Nope, I'll leave that for another time. Alright, thank you.